Hello, welcome back to the course on Polymeric Biomaterials. In the last few lectures, we have started looking at bulk behavior and responses, and we are going to continue that theme in this and the next couple of lectures as well. And in today's lecture, we are going to be looking at viscoelastic responses in polymeric biomaterials. Now, viscoelasticity is something that we have quite often hinted in this course several times, is a very important characteristic of polymers in general, particularly polymeric biomaterials when they are eventually used in a particular application. So, it is very important that we take some time to understand what the manifestations of viscoelasticity are, and also to understand how polymers can behave under different kinds of loads and deformations and so on. So, that is going to be the focus of today's lecture. So, as part of this lecture, we are going to be covering first, before we look at viscoelastic behavior per se, we are going to be focusing a little bit on breaking up that word into two words, namely essentially the elastic and the viscous behavior, and then try to ask how can we understand aspects of viscoelastic behavior from these two extremes in some sense and the entire spectrum in between. And we will look at a couple of very important viscoelastic manifestations, if you will, or tests, namely creep and stress relaxation. And closely related to those are the ideas of retardation and relaxation. And from an engineering concept or from an engineering perspective, we will try to see how to understand time scales in the problem of relaxation, for example, and then how to come up with a dimensionless number, namely the Deborah number, to help us understand what kind of responses may be dominant and when viscoelasticity can become dominant. And then towards the end of this lecture, we will focus a little bit on contextualizing the concepts we have learnt in this lecture and applying them to understanding the responses of biological tissues, particularly with a focus on collagen and its role in tendons, as well as the fatigue testing of tendons. With that, let us jump right into this lecture and first inspect what we think of as purely elastic and purely viscous behavior. Now, purely elastic responses, the first thing as we have already noted in our discussion on mechanical properties is for purely elastic system we are talking about time independent behavior, right. So, stress is only a function of the present strain, right, or any deformation that exists at that point in time is directly proportional to the load applied or the stress applied. It does not really matter for purely elastic responses how you got to that deformation, right. If you are at 5% strain, it does not quite really matter whether you got to 5% strain from 10% or you went from 1% to 5%, does not really matter, or even how fast you went up there. As long as you are talking about purely elastic responses, the contention is that stress is only a function of the present strain, essentially history and things like strain rate, what was the previous strain, all of this does not matter. So, any response or deformation response to the load is going to be pretty instantaneous, extremely rapid, very quick response. And because if you can recall that the elasticity, the property has to do with the ability for a material to store energy, these deformations are going to immediately vanish after the load is removed. So, once the load is removed, the deformations vanish almost instantly and the material goes back to its original state or shape. And like we have just said, this is associated with the properties of resilience or energy storage. Essentially, if you think about it from a polymer microstructure perspective and the kinds of bonds that you are working with, you are largely disrupting secondary bonds, right. So, these are non-covalent secondary bonds that are being disrupted, which can be formed and deformed without much effort, right. So, they can be deformed or disrupted and then formed again once the material goes back to its shape without any permanent effects, right. And that is the other aspect to keep in mind. Once the load is removed, the material goes back to its original condition without any permanent effects. And we saw that ideal solids will follow what is called the Hooke's law, where essentially stress is proportional to the strain, and ideal solids here, examples being perfect crystals or ideal springs and so on, where capital E is simply the modulus of elasticity. In some sense, it's one way to think about it is the ability of the material to resist deformation, right. So, the key here is the load and deformation are what are related through the elastic modulus. Now, this is the case for purely elastic time independent responses. Now, when you look at the other aspect of viscoelasticity, which is the purely viscous behavior, that is when time comes into the picture. Now, in viscous responses, like I said, they represent time dependent behavior. So, these are purely viscous responses, where when you apply a load or a stress on a fluid or a purely viscous fluid, what is going to happen is the molecules are anyway moving around randomly, and they will move past each other, and what will happen is you can't really lock in quote unquote the deformation, right, when you apply a load. So, deformation per se is not so meaningful to talk about for a purely viscous system, rather it is the rate of deformation that actually matters, right. So, stress in this case is directly related to strain rate rather than the strain itself. Unlike the elastic, purely elastic solids where stress is proportional to the strain, or load and deformation are related, here once you apply a stress, because you can't, like I just said, lock in deformations in any physically meaningful sense, what matters more here is the rate of deformation, and here stress is directly related to the strain rate. And deformation for such fluids will increase with time as the load is applied, and once the load is removed, the material or the fluid is not going to go back to its original position or shape. The deformation that has occurred is permanent, and that is because this is associated with energy dissipation. And idea here is because purely viscous systems are associated with energy dissipation, once the load is removed, any deformation that has occurred is going to remain permanent. And many commonly seen fluids reasonably follow what you would call Newton's law, which is simply given as stress being proportional to the rate of strain, or stress here being proportional to the strain rate, and the proportionality is removed through the property of viscosity. And this nomenclature simply, this epsilon dot simply indicates the rate of strain. That is what the nomenclature means. And some examples of such purely viscous systems are given here, and what you will see is viscosities here are quite different, right. Water viscosity is quite different from glycerol. For silicone oils, it could be a whole host of viscosities depending on what type of silicone oil you are talking about, but nevertheless they all reasonably behave as Newtonian fluids under most conditions where viscosity is only a function of temperature, right. In contrast, for non-Newtonian fluids, which we will not look at in this lecture, that will not be true, right. Viscosity could be dependent on other factors such as how fast you deform, etc., leading to other concepts such as shear thinning fluids, shear thickening fluids, and so on. But here we simply note that Newton's law is what we are looking at. For fluids that obey the Newton's law, they are called Newtonian fluids, where viscosity is simply a function of temperature. And just as we said that the elastic modulus is the ability of the elastic solid material to resist deformation, viscosity can be thought of as the resistance to flow, right. So, in that sense, one can think about them side by side. So, just to summarize, we are talking about fully recoverable deformations where stress is proportional to strain and is related through the elastic modulus for purely elastic solids, and we are talking about energy dissipation, right, in purely viscous fluids where the stress is proportional to the strain rate through the viscosity. In fact, the rate of energy dissipation is given as stress times strain rate, essentially it's given as eta, the viscosity times strain rate square. That's the rate of energy dissipation. So that's a good starting point for us to note before we proceed to understanding responses both for viscous and elastic type of extreme responses as well as viscoelastic responses. So with that background, we now start looking at the responses of purely elastic solids and purely viscous fluids. So shown here are two extremes where in one case we are first looking at purely elastic responses where a load is applied and as soon as the load is applied, an instantaneous load is applied, an instantaneous strain is achieved within the material which remains constant and persists as long as the load continues to be applied. That is what these two show. And notice here, as opposed to looking at stress versus strain, which we have seen in mechanical responses in the previous lectures, we are looking now at responses all as a function of time. Because remember, once you have the viscous component coming in, viscoelastic responses are better understood as functions of time, where deformations, loads, etc., all of that can change with time. So here what we are looking at is as soon as the load is applied, there is a deformation, and as long as the load persists, the deformation persists at a constant value, and as soon as the load is removed, the material goes back to its original position. Strain instantly goes to 0. That is the purely elastic response. Now in contrast, you have a purely viscous response as shown here. The same type of load is applied to a purely viscous fluid, and as long as the load continues to be applied, right, the deformation or the strain increases linearly with time as long as the load is present. Once the load is removed, the material, remember this is associated with energy dissipation, so the deformation cannot go back, I mean you can't revert it back to its original state. So any deformation that has occurred will persist thereafter. That is the case for the purely viscous response. Now if you have understood these concepts, we are in a good position now to ask, what does a viscoelastic response look like? And here we first note that all viscoelastic responses are going to be time and temperature dependent, and some manifestations of which we will see in this lecture. Essentially we are thinking of viscoelastic responses as being as having features of both elastic and viscous components, and that is one way to think about it. And our interest here is what you would call linear viscoelasticity, which is usually applicable for small deformations or small loads. Essentially you are not making any permanent changes to the microstructure of the polymer in applying these deformations, or as we will see later, we will talk about properties such as creep compliance and relaxation modulus. Both of which for linear viscoelastic responses will be a function only of time. It will not matter what the constant stress or the constant strain is, the history does not matter, only these properties will only be a function of time. So these are some assumptions we have made when we say we are looking at linear viscoelasticity, which is what we are going to look at in this lecture. Now because we have said that viscoelasticity can involve elastic and viscous components, one way to think about that is to look at extreme cases, or what you would call terminal responses, right. So essentially under what kinds of conditions will you get largely elastic behavior, under what kinds of conditions will you get largely viscous responses. So when you have high strain rates and or low temperatures, you see both time and temperature are coming here. When you say strain rate, there is a temporal connotation right there, right, and then low temperature, again temperature comes in. That is why we highlighted that viscoelastic responses are always contextualized against time and temperature. So when you have very high strain rates and or low temperatures, you largely get elastic dominant responses, and for very low strain rates and or very high temperatures, you end up getting largely viscous dominant responses. Now, this sensitivity to strain rate, that's sort of what we are hinting here. Put a pin on it. We will come back to it and look at it later when we look at tendons again, right? That's a very important, sensitivity to strain rates is a very important feature of viscoelasticity. Now, that context being said, now we can ask, what if I apply again a load such as shown here, that as a function of time, and then track what happens to the deformation. So, what you see here is you appear to have some features of both elastic and viscous components, but then there are some new features as well. So, we will spend a minute or so to look at this in some detail. So, initially when a sudden load is applied, it seems that there is a sudden jump in deformation, sort of indicating perhaps an elastic dominant kind of a response, but thereafter what you see is the change, that is the deformation as a function of time is changing, right. The rate of strain keeps changing with time, but in this case what we are doing is, after a certain point in time, we are removing the load, and then what you see is you are sort of getting, in the initial stage at least, a sort of a quick drop in deformation followed by a gradual drop. So, if you piecemeal analyze this curve, this is what you would call elastic deformation. This is viscoelastic deformation. This is elastic recovery, and this, as would be clear by now, is viscoelastic recovery. And this is just one sample of a potential viscoelastic response, right. We have not specified the material type, we have not said whether it is a thermoset or a thermoplastic, we have not said what the temperature is, etc. So, this is a classic textbook example of a viscoelastic response, right. Now, having broadly looked at the extremes, namely the elastic and viscous responses and also the viscoelastic response, now we are in a good shape to understand viscoelastic behavior based on two important testing. One is creep, the other is stress relaxation. So, first we will look at creep. Remember, we have already said strain rate sensitivity is a very important aspect of viscoelasticity. Now, we are going to look at two other aspects which are characteristic features of viscoelasticity, namely creep and stress relaxation. So, creep essentially is when you apply a constant stress that is suddenly applied to a material, and the resulting strain is studied as a function of time, right. Again, remember, we are looking at properties that change with time, right. So, the load is applied and the load is held constant. At constant load or constant stress, how does the deformation develop in the material? That is what we are trying to ask. And again, as always, before we look at the viscoelastic response, it is instructive to quickly look at the purely elastic and purely viscous responses. Now, if we look at a purely elastic response, as soon as the spike sudden stress is applied, the strain will develop instantly and will remain a constant, as we have already seen, right. Because you have no mechanisms involving energy dissipation, this is essentially energy storage. Once the load is removed or once the stress is removed, the strain instantly goes back to 0 and you get fully recoverable deformation, right. So, that is the purely elastic response. The purely viscous response, as we have seen, strain is going to linearly increase with time with constant stress, and remember, the stress itself is not changing with time. You have applied a certain stress and you are holding it constant. At constant stress, strain linearly increases with time, and then after stress is removed, the deformation is going to be permanent. Now, if you want to now look at viscoelastic response, what is the situation? So, here as we have just seen, this is just one example. The strain may jump initially and then follow a non-linear increase, right. This initial spike may be related to what you would call an elastic dominant kind of a feature showing up here, this is sort of an exaggerated picture, but largely what you will get is something that looks like this, right, where the slope here is higher, and as time goes by the slope keeps dropping. This is strain versus time. The slope keeps dropping, and this is what is called creep. At constant stress or constant load, which does not change as a function of time, deformation continues to increase with time, right. Of course, non-linearly, because it is not purely viscous either. Remember, if it is viscous, it will linearly increase with time. This is non-linear increase because it is a viscoelastic response. And depending on the material, this can either plateau off. For example, in thermoset, you might get a response that looks like this, whereas in a thermoplastic, it might eventually reach a constant rate and just keep increasing with time, because the chains etc. can move around and slide past each other, right. But if you now let go of the load as shown here, if the load is removed, stress is removed, you get what is called creep recovery, which is simply deformation recovery after the removal of stress. After the load is removed, you get creep recovery, but essentially you see even here the deformation does not again go back to its original, the material does not go back to its original shape, right, because you have viscoelastic materials, you get some recovery in the deformation or what we call creep recovery, but then permanent deformation typically continues to persist. And one way to think about this experiment, if you had to visualize it, is if you take a piece of plastic, right, like a polyethylene bag or something, right, cut out a strip and then you affix one end of it on one side and then you hang a weight, right, on the other side. Now the weight has to be reasonable, it should not snap immediately, but if the load is reasonable, that you hang it, and what you are looking at is you will see some immediate elastic like response in deformation. So you will see a quick deformation initially, but then if you track it over time, come back every day and measure it with a ruler, you will see that under a constant load or a constant stress, the material will continue to deform, right. Apart from the initial deformation you got, which is largely the elastic kind of a response as shown here, you will see an immediate elongation, but then with time over many days you will see slowly the deformation will continue, right. And if you remove the load, you will see some kind of a recovery as shown here. And because properties change with time here, it does not make sense to talk about time invariant properties such as modulus of elasticity or viscosity. What we would rather look at here is a response function which is called creep compliance, which if it is a tensile load is given as d of t, with shear load it is given as j of t. Essentially this is the inverse of modulus. And they are simply given as at any given time the creep compliance is strain at that time over the constant stress applied. And like we just said on a couple of slides ago, these are functions only of time because we are working largely with linear viscoelasticity, right. So creep compliance is one way for us to understand long-term deformation to a constant stress for a viscoelastic material. And where this becomes important in biomedical applications is in an example where we are looking at PEEK. This is not a polymer we have looked at much in this course, polyether ether ketone. They are used as fusion cages in intervertebral disc replacements, essentially placed between vertebrae to restore disc height and maintain the spine alignment. And once you have placed it there, it is going to be under constant compressive load, not unlike the example we have seen on the slide because of the body weight, and over time, over many months, creep can set in, leading to misalignment, right. Now, one thing I would like you to stop here and maybe ask or look up is, one, why is PEEK the material of choice for such an application, right. So, why PEEK? And if you have understood all the structure property relationships we have been looking at throughout this course, if you are able to look at the structure of PEEK, the properties of PEEK, then it should be fairly clear to you why PEEK is one of the choices for this kind of an application, right. The second question you can ask is, if it undergoes creep, what are some strategies to mitigate that? This is the limitation. So, what is the strategy to mitigate? The first one is more of a scientific question. The second one is more of an engineering question, because here you are asking from a design perspective, what do I need to do to ensure that creep isn't significant once I have implanted, right. So, that is creep. Now, we will move on to stress relaxation, which is the other very important feature of viscoelasticity. So, here what is happening is you have the same viscoelastic material, and then what you are doing here is a sudden strain is applied, a deformation is applied suddenly, and the deformation is held constant as a function of time, as shown here, right. This constant deformation is applied suddenly, and as a function of time it is held. And what you are tracking here is you are tracking the stress required to hold that strain over time is tracked, right. So, in creep you applied a sudden stress and you tracked strain over time. Here in relaxation you are tracking stress over time in response to a suddenly applied deformation which is held constant over time, right. And again we will first look at the purely elastic and purely viscous responses for contextualization. So, as should be very clear to you by now, a purely elastic solid, what is going to happen is as soon as the deformation is applied, the stress develops instantly and remains constant, and as long as the deformation persists, the stress is going to persist within the material, right. But once the strain is removed, the stress instantly is going to go back to 0. Again, some of these things are thought experiments in some sense, because when we say a sudden strain is applied, now you can show these kinds of plots here on paper, but in reality in an experiment it is going to take a finite amount of time for any instrument, no matter how small it is, to apply that sudden deformation, right. So, some of these things have to be understood with a little bit of caution, especially the purely elastic and purely viscous responses. What you are talking about is sort of the extremes as thought experiments. In fact, in purely viscous, you can't even achieve instantaneous strain, because remember, in a purely viscous system, once you have applied a strain, and what matters is stress is proportional to the strain rate, right. And because in stress relaxation experiment, strain is not changing with time, any stress that is instantly developed, right, any stress spike response that is seen in response to this sudden deformation, that is going to instantly drop to 0 because of instant dissipation, right. That is not going to persist at all, right. So, that is the purely viscous response. Now, what is the scenario for a viscoelastic response? Here what you see is, you see that with time the stress is going to decay. Again, remember, the deformation is held constant with time, that is not changing. For a constant deformation as a function of time, the stress is going to decay or reduce within the material, right. And this residual stress remains until the strain continues, and even at very long times the stress typically does not go to 0, but again that depends on the type of material, the temperature you are operating at, etc. For example, for thermosets, because again of crosslinks, etc., you will have some residual stress typically, and perhaps for thermoplastics at very long times they may go to 0 at time tends to infinity, right. So, these are some ways to think about stress relaxation for the different kinds of materials. And just as we saw creep compliance for creep, here the response function, again it makes sense to talk about time varying properties. So, we are looking at relaxation modulus, where again E of t if it is tensile, G of t if it is shear, This is just depending on the type of deformation that is applied, type of load that is applied, where it is simply the stress at that time over the constant strain that is applied. And this captures quite well the stress decay that occurs within the material over time. Now, if you had to think about a physical experiment to visualize this kind of a relaxation, perhaps you can think about taking a rubber band and pulling it taut and holding it or wrapping it around a hard-bound book, for example, right? So you're pulling a rubber band taut and putting it around a hard-bound book and leaving it like that. So what you have done is you've applied a fixed constant deformation, and you're letting and you want to track the system over time in terms of how the stresses relax. And what you will find is after a very long time, you will start to see that the rubber band will start to loosen up a bit, right? And that's one manifestation of what we are looking at here. And in the biomedical context, more useful in a course like this, one example where you can see this is these polyurethane orthodontic ligatures or bands, which are used to tie arch wires to brackets and hold them in place for your teeth. And typically, they are polyurethane where you can get them colored, right? Typically, if they are stainless steel or metal, they are usually not colored. But if you have some aesthetic preference, you can actually opt for polyurethane and get colored ligatures or these bands that hold the arch wire to brackets. And when held at a constant deformation, the internal stresses can decay over time, leading to ligature slippage. Right? So that's one manifestation in a biomedical context for a polymeric biomaterial undergoing stress relaxation over time in response to a constant applied deformation. Now, two related concepts that we will see are related to creep and stress relaxation are retardation and relaxation, and we are trying to understand it from a molecular perspective or a physical perspective. Retardation first may be thought of as a delayed elastic response, right? Essentially, the retardation time essentially can be thought of as the time scale over which the creep strain accumulates. Now, if you take purely elastic materials or solids, there's going to be an immediate spike in strain with stress, but that's not the case for a viscoelastic polymer, right? You're going to have a response that occurs with some delay, and that delay or the delayed quote-unquote elastic response can be thought of as retardation, where the creep is not instantaneous but slowly progresses over time. And even after removal, you get slow creep recovery, but again not full recovery also. So it has some features of elastic materials, but also time comes into play where the creep increases non-linearly with time after an initial spike perhaps, and then even recovery is not complete, right? It happens slowly and doesn't even go to completion in many cases. That's retardation. And typically a short retardation time typically means more rapid the creep strain. Now, relaxation essentially one can think about the internal stresses or tension being relieved over time because of some molecular processes. For purely viscous fluids, molecules move about extremely rapidly to take up new positions, which means the relaxation is going to be almost instantaneous, right? Whereas in the case of elastomers, what you can have is restricted mobility where the segments take longer to respond. So if you stretch and release rapidly, you don't give sufficient time to rearrange, resulting largely in elastic behavior, right? Again, you see, we are talking about time scales here, and that's going to come up again in just a bit when we talk about Deborah number. You are talking about stretching and releasing rapidly. So there is a time scale associated with the stretching and releasing rapidly. And you are talking about a time scale required for rearrangement, molecular rearrangement within the polymer itself. And in polymers, you can have multiple relaxation time scales depending on what length scale you're talking about. You can have it go from bonds to segments to chains, etc. Whereas if you stretch slowly and continue to maintain the strain, these relaxations can occur, resulting in viscoelastic behavior. So far we have only looked at conceptual understanding of viscoelasticity as it is pertaining to polymeric biomaterials. If you are interested in more detailed aspects of viscoelasticity, here is one suggested reference text that could serve as an introductory textbook to understand polymer viscoelasticity. Now, we've just talked about time scales when we talked about relaxation. So, we'll continue that. That's a good segue for us to talk about what we would call the Deborah number. Now, this is a classic engineering approach. When you have two time scales, then one question is, can we take the ratio and try to understand extreme responses, right? Under one situation, in one extreme, what kind of a terminal response do you get? In another extreme, what kind of a terminal response do you get? And an entire spectrum going from one end to the other end, all the way in between, right? And that leads us to this idea of a Deborah number. So first we will note that for elastic solids, right, any relaxation that can potentially occur is going to take an infinite amount of time. Essentially, for any time scales that are meaningful, elastic solids don't show any relaxation at all, primarily because they are associated with the ability to store energy, right, not to dissipate. Whereas for viscous fluids, the relaxation is almost instantaneous, right, because they are associated with dissipation. And polymers, like we have said repeatedly, you can have relative viscous and elastic contributions resulting in relaxation timescales depending on what you are interested in. Like we just said, you can have bonds, for example, at that length scale, vibrations, right, rotation, all of this can have timescales associated with it. Then you can have segments, right, then you can have chains, then you can have multiple chains, so chain motion, entire chain motion, right. So depending on what kind of length scale you are interested in, you can have a multiplicity of relaxation timescales. What we are talking about is an average value here. Now, what we want to be able to do here, and just based on what we have said, this should be pretty clear. What we want to be able to do is, we want to ask, in the time frame that I am interested in, or in the time frame of the experiment, or in the time frame I am observing the material, is relaxation dominant or not, right? So in other words, in comparison to the time scale of observation or time scale of the experiment, what is the time scale of relaxation, right? And that so happens is can be quantified beautifully by this idea of a Deborah number. Essentially what you are asking is viscoelasticity dominant and to what extent, particularly with respect to relaxation, and the Deborah number is simply given as a characteristic relaxation time scale given as lambda over the characteristic experimental or an observation time scale. And why it is called the Deborah number also has an interesting history. This was essentially coined by Marcus Reiner. So he was a visiting faculty at Polytechnic Institute of Brooklyn in New York, which incidentally is the place that Hermann Mach, whom we have seen when we discussed polymer crystallinity, migrated to when he was escaping Europe during World War II. So that was an important center for many scientists. So nevertheless, Marcus Reiner was a visiting faculty there, and in a conference that was held in 1963, a rheology conference, in an after dinner talk, he introduces this idea of a Deborah number, and it was later published in Physics Today in 1964. And the inspiration comes from a very interesting source. So what we have here is a quotation from the Old Testament, the King James Version, where the prophetess Deborah is said to have remarked that the mountains melted from before the Lord. Now what that means has to be contextualized a bit for what we are looking at here. What does it mean when we say mountains melted? What that essentially means is, over geological timescales, over extremely long timescales, mountains can also have fluid-like behavior or can relax. Essentially, and this can be understood based on tectonic activity and so on. So essentially, a solid, what appears as a solid rock or a mountain, when observed over extremely large timescales, can relax, right? Can attain fluid-like properties and show relaxation, right? So that's sort of the inspiration that led Marcus Rayner to come up with the idea of a Deborah number. So what does it physically mean? What does a Deborah number mean? So if relaxation occurs very, very fast, or if the time scale of observation is very long, right, then the Deborah number essentially goes to 0. Or more practically, if the Deborah number is much less than 1, you get the terminal response of a viscous liquid-like property. In contrast, if you have relaxation that occurs very slowly, right, or if the time of observation is extremely short, then you essentially get Deborah number tending to infinity, or more practically, if Deborah number is much greater than 1, you get more terminal elastic solid-like responses. And when the time scales are reasonably comparable, that's when you get viscoelastic effects based on the relative contributions of the viscous and elastic components, which depend both on deformation rate and temperature. Deformation rate we have looked at quite a bit, not just in this lecture but in previous lectures as well. Temperature is also something we have looked at quite a bit, and I would like you to pause and reflect on this. Now, how does all of this depend on temperature? Now, one hint I'll give you to think about this is, if you think about either the weight hang experiment from the polymer strip, which we saw for creep, or the rubber band tied around textbooks for stress relaxation, you can now ask, if I conduct those experiments on in very cold winter months versus very hot summer months, what kind of differences would I see, right? What would be the time scales associated with relaxation, right? How fast will creep proceed, and how does all of that relate to the temperature itself, namely Tg of the polymer. So again, you have to connect it back to Tg vis-a-vis the operating temperature, right? So that's one way to think about the effect of temperature. Now that we have a reasonably good understanding of viscoelasticity, we will now try to see, in the remaining time that we have, how to contextualize all of this for biological tissues and biomaterials. We'll first note that the mechanical behavior of most tissues are a result of the structure properties of the constituent molecules, some of which we have looked at in quite some detail, and we will again revisit on this slide. Again in biology, the idea of hierarchy becomes very important. When we looked at collagen and many other biomacromolecules, we saw that hierarchy played a very important role there. Of course, the properties also will depend on the density of the tissue, age of the person, where it is located, degree of hydration, a host of other factors. Now, two important, from a polymer perspective, two important biomacromolecules that become important are collagen. Again, idea of hierarchy comes here, which is essentially a structural protein with very high tensile strength and is one of the primary load-bearing elements in many tissues, including blood vessels, skin, tendon, ligament, and so on, right? Of course, you also have elastin, which is elastomeric, or a rubber-like material or protein in connective tissue, responsible for things like skin elasticity, blood vessel recovery during blood flow, and then lung expansion during breathing and going back to its original state. Again, you see elastomer-like properties. So these two become very critical. And any differences that you can perhaps see across tissues can be ultimately tied back to the properties of the extracellular matrix or ECM, of which collagen is one of the primary components for many tissues, and elastin, of course, depending on the type of tissue. For example, in response to strain, you can have reorientation of the collagenous matrix, as we will see very shortly for tendon tensile testing. Of course, the mechanical properties are also tissue specific, depending on what other kinds of molecules and factors are present. For example, in cartilage, you will have type 2 collagen associated with proteoglycans, right? That gives a certain type of mechanical properties. In bone, you will have mineralized collagen, essentially some kind of a apatite, some kind of a calcium phosphate mineral associated with collagen. That's the inorganic matrix associated with the organic collagen that leads to its specific properties. You can also have collagen orientation, right? In bone, it's a pretty randomly oriented collagen network that you have, whereas in ligaments and tendons, which are more anisotropic, you will have pretty aligned collagen fibers. So all of these things will contribute to the mechanical properties. And again, all of this is not new to us. We are simply recalling some of these concepts in the context of mechanical properties in viscoelasticity. We have looked at all of this in great detail as part of structure property relationships in lectures 19 and 20, which I would like you to pause and recall at this stage. And just taking collagen as an example, you can have factors affecting elastic modulus and strength. For example, cross-linking, which is another important aspect. Apart from hierarchy in collagen, cross-linking plays a very, very important role, particularly during maturation, in contributing to the excellent mechanical properties of collagen. Whereas, in contrast, during aging, damage to collagen can lead to weakening of these properties. And likewise, lack of mobility can lead to tissue atrophy, whereas exercise within some constraints can lead to more production of some of these extracellular matrix components to deal with repeated loads, right? Muscle building, for example, relies upon some of these ideas. So largely because many of these are what you would call mechanosensitive tissues, right? Mechanobiology is an entire area on its own, and factors such as viscoelastic effects play a very important role. How collagen, the interplay between collagen and proteoglycans, for example, will play a very important role in how cells sense and feel mechanical forces around them. So now we will look at very briefly the example of tendons and the mechanical response. Tendons are essentially tissues that connect muscle to bone and help effectively transfer the force generated by muscle contraction to the bone, right? That's what tendons do. There are a whole host of tendons in the body, and they take up different names based on their location, etc. Our interest here is the mechanical properties, right, or viscoelastic aspects of tendon testing. And what we are showing here is a stress strain curve of tendon, which exhibits what you would call a classic triphasic stress strain behavior, right? What that simply means is there are three distinct regions that can be identified. That's what the triphasic means, where roughly you're talking about 1 to 4% being called the toe region, 4 to 6%, again these are ballpark numbers, which should call the linear region, and 6 to 8% roughly strain you would call the yield region, and beyond 8-10% you get failure. Essentially you will rupture your tendon. So let's quickly look at what's happening in each of these three regions. And of course, to contextualize this, largely we are showing that this is sort of the physiological range over which you operate. For usual walking, regular activities, you will not typically cross 3-4%, right? That's about the limit. Whereas for heavy exercise, etc., you may stretch it to about 6% or so, right? You're still within the linear region. That's the point we're trying to make, even for extreme physiological loads. Of course, if you go to the yield and beyond 8-10% strain, you're going to rupture, right? So the first thing you note is that there exists a non-linear toe region, and this is another very key aspect of viscoelasticity. So we've already seen strain rate sensitivity, we've seen creep, we've seen stress relaxation. We're now looking at non-linearity in the toe region, which is another very important aspect of viscoelasticity. Essentially what is happening in this region is some water is removed, and because tendons have are anisotropic tissues, essentially what that means is you will get different mechanical properties depending on how you test them. You will get different properties based on whether you test them transverse or longitudinal, etc. And because of the function in the body, tendons typically will have collagen fibers that are not just largely aligned in one direction, right, the direction of load, but they will also have what you would call the crimping pattern, this crimped kind of a pattern. And what is happening in the toe region is these crimps largely get straightened out with time, slowly, right? Again, gradual time dependent straightening. That should indicate to you that viscoelastic effects are at play here. And straightening of the flexible areas in the collagen triple helices, right? And this crimping pattern is so important that a lot of engineering strategies will employ biomimetic approaches. Now, biomimicry is a word we have seen in one of the earliest lectures in this course, and because the crimping pattern contributes to these kinds of properties in collagen and in tendons, many engineering approaches to make replacements, right, tendon replacements, etc. If you do a quick search and look for biomimetic approaches, you will find that many of them try to recapitulate the crimping pattern. Now, if you go to the linear region, essentially here force is directly translated to the molecular strain for the aligned collagen molecules and fibers, right. So, you are essentially in the linear region, and this is not hard to understand, right. And typically because you are in the linear region, it does make sense to talk about perhaps Young's modulus, and it can be as high as about 1 or 2 gigapascals. That's sort of the number you're talking about for tendons. And of course, if you go to the yield region, you're going to get permanent deformation arising from microstructural damage. So that could include things like unfolding of helices, slippage, accumulating damage in the collagen fibers, lots of factors, right, leading to a lot of pain. And in exercise, perhaps very heavy exercise, you're probably relying upon small microstructural damage every now and then, leading to more repair and deposition mechanisms that build collagen, right. But of course, if you've gone well into the yield region, then you have things like slippage and then accumulating microstructural damage that just continues. And again, notice that we are using words like yield, slippage, which are all words we have used in lecture number 22, where we looked at the yield region in tensile testing. So these are not new concepts, we are just contextualizing this for biological tissues. Of course, when you finally go to the failure region, that will involve the breaking of crosslinks and complete rupture. And a large part of this can be understood from understanding the hierarchical organization and anisotropy in tendon, right. So this is something that you can pause and look up very quickly. Tendon is hierarchically organized, as with many other tissues in the body such as bone and ligament. Tendon too is hierarchically organized, which means you're going to have multiple length scales that build up, right. You can have collagen molecules that go assemble to fibrils, that assemble to fibers, that assemble to fascicles, and eventually to tendon. So you have many different levels at which you can talk about structure build-up, and the length scales over which this occurs is actually mind-boggling. You're talking about something like, for a collagen molecule, you're talking about 1.5 nanometers diameter, all the way up to a tendon, which is about 0.5 to 1 mm dia. So you look at just the length scales over which the hierarchy spans. That number itself, that range itself, is quite amazing, right? And of course, there is anisotropy. Like I said, you have aligned collagen fibers with the crimp pattern. So that is a good, gives you a good understanding of how both hierarchy and anisotropy in tendons eventually leads to its mechanical properties. So again, structure, property, and how this together leads tendon to perform its regular activities, right. So this structure, property, performance paradigm is going to follow us throughout the course. No matter what topic we are discussing, this fellow is going to just keep following us. So we might as well try and stop and appreciate it whenever we can. And in closing, we want to offer a few comments on viscoelasticity in biological tissues, right. Now, viscoelasticity confers a lot of benefits in biological tissues. So, for example, it helps tissues adapt to varying or repetitive loads. Tendon, ligaments, etc. have to undergo repetitive loads, right. Maintain structural integrity. For example, in cartilage, right, where compressive loads are significant, structural integrity becomes important, right. And when cartilage starts to degrade, that's when you start to get things like osteoarthritis. And of course, protect against sudden impacts, right. And some potential benefits are listed here. So if you have relaxation, for example, that can reduce tissue damage during prolonged loading. And the example given here is reducing the risk of ligament sprains. So with a ligament, it's a sprain. With a tendon, it is a strain. This is oftentimes a point of confusion for many people. Ligament is associated with a sprain, tendon is associated with a strain. And of course, it also allows tissues to adapt to sustained deformation without causing damage by relieving built up stresses over time. So these are just examples of both creep and stress relaxation mechanisms at work. Within certain limits, they can be quite beneficial, for example, in muscle, skin, blood vessels, etc. Of course, this can also lead to potential issues. For example, you can have extensive creep in ligaments or gradual deformation over time leading to creep, resulting in ligament laxity. Now, this becomes important because if you are designing materials or polymeric materials that can replace ligament tissues or ligament replacements, not only are you looking at things like modulus and crimping, etc., you are also thinking about what happens when I hold this to a constant load, and what is the effect of creep there, right. So, you do not want the material to undergo significant creep and result in loosening of the the ligament itself, right. Of course, you can have other kinds of chronic stresses, for example, in blood vessels leading to damage and rupture. Essentially like an aneurysm, where the blood vessel in some places where there is extensive stress concentrations, it can bulge out and eventually with enough force it can rupture, right. That is what an aneurysm is. So, these are some potential issues that you can see with viscoelasticity, but again, depending on the context, depending on the time frame, depending on the temperature, depending on the location, all of that viscoelasticity has to be understood and contextualized. Now, one last aspect of viscoelasticity that we will see is fatigue testing and hysteresis. Now, we hinted at the idea of repeated loading and unloading, right, and that is what fatigue testing is, where you are repeatedly loading a material multiple times at a fixed amplitude. The load is definitely lower than the strength, but in every loading cycle you are slightly accumulating some microstructural damage, right. So, what you will see is viscoelastic deformation resulting in energy dissipation and slowly accumulating damage, leading to hysteresis. So, that is the last property that we are seeing in this lecture associated with viscoelasticity. Strain rate sensitivity, creep, stress relaxation and hysteresis. These are classic textbook examples of viscoelasticity. So, what you see here is a force versus strain or a stress versus strain curve for tendon fatigue testing, and you are determining the number of cycles to failure. Even tendon, for example, if you want to think about strain sensitivity or sensitivity to strain rate, right? The faster you pull, if you pull a tendon very fast, you will get a stiffer response, right? That has to do with strain rate sensitivity, right? That's something that's classically seen in tendons. Anyway, so here what's happening is in every cycle you have these hysteresis loops that are indicative of energy dissipation, and in every cycle you keep pushing to the right where you go from a crimped toe region to a linear region, towards the end of which you start accumulating some kind of small microstructural damage, which tends to accumulate over time, perhaps due to overuse in regular context or in testing over many cycles, leading to ultimate rupture. So you see, within about 8-10% strain, you're starting to sort of break off. By 10-12%, you completely rupture the tendon, right? And that increased hysteresis is related to collagen damage. So from a design perspective or from a biomaterials perspective, what you want to ask is, if I want to design a polymeric material, this is a very important mode of testing for tendon ligament replacements, right? So with that, I hope you get a good sense of what viscoelasticity in general is, some conceptual understanding of manifestations of viscoelasticity, and then trying to understand how all of that can be contextualized to biological tissues and polymeric biomaterials.